Hello, AP Chemistry students, and welcome to Solubility Equilibrium. This is exercise 5 on page 5 of the NIMSY packet. I am Mr. Regan. That is me. And we are going to work through a problem that you might think is difficult. It combines a lot of different topics we've been talking about this year. And so let's get started. What we want to think about here is this idea of Q. And Q and K are very similar. It's the same idea, and they have the same formula that K or Q is equal to your products over your reactants. K is at equilibrium, whereas Q is at any other time. So Q might be right before equilibrium, Q might be right after equilibrium. It is equilibrium just at another time. So, it's the same K. So what we want to look at here, if I get rid of these, is that we want to think and compare K to Q. And we did this in the previous part of this unit, where we compared K to Q, and we figured which way the reaction would go. Would it go forward? Would it go backwards? Or would it simply be at equilibrium? And we're going to use that same concept this time to determine if a solid or precipitate will form. And I crossed this area out over here because I like the K before the Q over here because it is alphabetical. So K comes before Q in the alphabet. And we're saying that if K is greater than Q, we want to say that if the K is greater than Q, we write that just like it is, and we put a line to connect an arrow. And so this would be going, if we look at the reaction below, if our arrow is going to the right, that's going towards the aqueous things. And if it's going towards the aqueous things, then no precipitate or solid forms. However, if it goes the opposite way, where K is less than Q, we have our arrow again, and it's going backwards, and in this case it's going towards the solid. So a solid precipitate, PPT for short, forms in this case. And so that's what we're going to do. We're going to be able to compare a Q and a K value together. And if the Q is greater than the K, a solid will form. And if not, then our ions will just be dancing and bouncing around in solution merrily and happily. And so let's take a look on the next page and start this problem. So what we have here is that we have a solution that's prepared by adding 750 milliliters of this cerium-3 nitrate. And we are adding it to 300 milliliters of potassium iodate. We want to know if this cerium-3 iodate will form a solid. And so the first thing that we need to do here is write a general equation for this. We have a type of reaction here where we have two things, AB plus CD, and that should make AD plus CB. And this is a double replacement reaction. And not all the times are we going to form solids, so this might be a solid from past experience, but we can actually figure out if it will form a solid now by comparing our Q to our K. And so let's write out our formula here. We first have CeNO3 plus KiO3. We take our outsides, join them together, and our insides. CeIO3 3, because the charge on our cerium was +3, plus insides KNO3. I need to balance my equation knowing that I had 3 NO3s. Now I make 3 Ks, and my 3 IO3s match up over here. So now I have a balanced equation, and I can look at what I'm doing. So I have this information here. I have 750 milliliters, or 0.75 liters, of 4.00 times 10 to the negative third molar. And for the potassium iodate, I have 0.300 liters, simply because 300 milliliters divided by 1,000 is 0.3, and this is 2.00 times 10 to the negative second molar. Now what I'm doing is I'm adding these together, and this is going to bring about a new concept. This concept being the idea of additive volumes. If you are to add really red Kool-Aid, oh yikes, oy, Kool-Aid to watery Kool-Aid, the color is going to be somewhere in the middle. It's going to be like a pink color Kool-Aid, because the two volumes are additive. We count all the water from both of them. There's not a lot of water in this first one. There is a lot of water in the second one, but the amount of water still makes a difference. So if I want to think of this solution having additive volumes, I just want to add them up. So this is going to be 0.750 liters plus 0.300 liters, and that's going to be 1.05 liters as my volume. And so this idea is going to be important here, because I'm going to want to get a molarity using this value, and I'll show you that on the next page. So at this point, I want to break up my ions. And the first thing that I had was my CeIO3 3. Excuse me, CeNO3 3, and I also had KiO3. Now what I'm trying to form here, or see if I'm forming, is CeIO3 3. And if we use our ion knowledge here to break this up, we know that this will be Ce plus 3 plus 3 IO3 minus. So we're just breaking this up. Now we want to know if this forms a solid. So we need to figure out, the KSP for these things. So the only parts of the compounds above that I'm going to need are my Ce and my IO3. So when we break this up, this is going to be Ce plus 3 plus 3NO3 minus, and this is going to break up into K plus plus IO3 minus. And so we won't need the K plus or the NO3 minus, and so we're just looking at these ions. And if we look here, this is going to be a 1-to-1 ratio, and so is this. So 1-to-1-to-1 ratio. So whatever my concentration of KiO3 is, that's the same for my IO3 minus. Whatever my CeNO3 3 concentration is. That's my Ce plus 3 ion concentration. Excuse me. And so I'm going to now write these on the next slide. So I was told from the first bit of information over here what the concentrations and how much of those I have. And so I'm going to start breaking that down on the next page. So we said that Ce, and I'm just going to show this one more time, CeNO3 breaks down into Ce plus 3 plus 3NO3 minus, and that this is 1 to 1 to 1. Or I'm sorry, 1 to 1 to 3, but I don't need this. So whatever this information is, it's the same as that. So here is the data that I had. I had 4.00 times 10 to the negative third moles per liter of this CeNO3, but I can just say that that is of the Ce plus 3 1-to-1 ratio. At this point, I'm trying to figure out the new molarity of this Ce plus 3 ion. I'm trying to figure out what its concentration is in moles per liter. But because I added this new solution, there's more water in there, and I need to consider this additive volume now. So if we go one more step in our fence post here, we know that initially in the 0.750 liter container, this would be how many moles we had if we multiply that value. If we want to know how many moles per liter we have in the new additive solution, we need to get the liters back again, and so I put that additive volume on the bottom. And now I can get a molarity of my Ce plus 3 that is now in solution. And that value is going to be 2.86 times 10 to the negative third molar. I'm going to do something similar for the IO3 minus, and that is 2.00 times 10 to the negative second moles per liter of IO3 minus. And in this case, this volume was just 0.300 liters. So now I have the moles of IO3 minus, but I want to find out the molarity in the whole additive solution now. And this turns out for my IO3 minus to have a concentration of 5.71 times 10 to the negative third molar. So now I have good information. I have a newly acquired concentration for my Ce plus 3 and my IO3 minus. Because again, I was trying to figure out whether CeIO3 solid will form. And so I can think of my KSP equation now that I know these concentrations, and I can get a value for Q. And so let's do that on the next page. So here's my equation again. CeIO3 solid will break down into its component ions, which are Ce plus 3 plus, importantly here, 3 IO3 minus. And I don't need this x and 3x this time because I just solved for my values. And so if we take a look on the previous page, our values for Ce plus 3 are 2.86 times 10 to the negative third And my IO3 minus is 5.71 times 10 to the negative third. And importantly, I need to remember this coefficient goes up top. I have to cube that value. I can't forget to do that. And so my KSP, my QSP is going to equal this value here. So I'll rewrite that. QSP equals 2.86 times 10 to the negative third times 5.71 times 10 to the negative third cubed. And my Q value is 5.32 times 10 to the negative 10th. Okay, wow. I got a value. But that still doesn't answer, will a precipitate form? So now that we've finally got our Q, we need to do the one last step, which is compare K to Q. And so we'll do that on the last slide. So let's think alphabetically here. I have my K, I have my Q. I just solved my Q to be 5.32 times 10 to the negative 10th. And my K from the first page of problems was 1.9 times 10 to the negative 10th. 1.9 times 10 to the negative 10th. And so because we know that these have the same times 10 to the 10th, we can just get rid of that and more simply compare 1.9 to 5.3. We'll get rid of this 2 for comparing sig figs. And we now know that Q, the value 5.3, is greater than the value 1.9. We connect a line to form an arrow, and we can say from before that if we have CE IO3 solid in equilibrium with the ions in aqueous, that my arrow will go backwards towards the solid. So yes, a precipitate forms. This is a difficult problem. It requires a lot of steps, but once you get the patterns down for how to solve it, it becomes pretty easy. Please email me if you have any questions. I hope this helped, and I'll talk to you and see you soon. Thanks.